Hello, everyone. I'm Seyed Marvasti-Zadeh, a postdoctoral fellow at the University of Alberta. I will present our paper titled Training-Based Model Refinement and Representation Disagreement for Semi-Supervised Object Detection in collaboration with Professor Nilanjan and Professor Nadir Erbilgin. First, let's start with our problem overview. As we know, object detection has seen remarkable advancements thanks to the availability of extensive benchmark datasets that provide class labels and bounding boxes for various objects. Collecting and annotating object detection datasets can be quite challenging due to their expensive, time-consuming, and labor-intensive nature. Additionally, the lack of domain experts and limited resources further complicate this task. On the other hand, unlabeled data is a valuable resource that provides insight into the distribution of data. It offers the opportunity to learn strong representations that can effectively handle various transformations. Semi-supervised object detection aims to improve the performance and generalization of existing object detectors using a combination of limited label data and extensive unlabeled data. The common approach involves jointly training two networks called the teacher and the student. In this approach, initially a base detector is trained using available label data during the burning stage, and subsequently, during the semi-supervised learning or SSL stage, pseudo-labels are generated to train the student, and teacher is gradually updated using classical exponential moving average. However, this approach comes with some limitation. The first limitation is manually defined EMA decay, which results in insensitivity to changes of the student weights and also suboptimal performance. The second challenge is consensus problem, which means losing the distinctiveness of teacher and student model at the latter stage of the training procedure when two models become almost identical. Finally, addressing the issue of noisy and misleading pseudo-labels is crucial. These labels can impede the accurate optimization of models and result in an effective learning from unlabeled data and also slow convergence. To overcome these challenges, we introduce a novel approach with two primary objectives: dynamically refining the weights of the teacher and student models and keeping these networks diverged during the training procedure. Our method consists of three stages. In burning stage, we do the same to train base detector using limited label data. Next, we train the student using pseudo-labels for n iteration. Once completed, we freeze the weights of both teacher and student networks and learn a set of lightweight scaling operations assigned to the learnable parameters of both models for m iterations. Finally, we iteratively apply the SSL and TMR states until the training process is complete. Since our approach is general, we have integrated it into two versions of well-known unbiased teacher object detector. Also, we incorporated cascade regression into our baseline. This integration can provide more reliable pseudo-labels and effectively mitigate overfitting problem. As I mentioned, during the TMR stage, we first apply a scaling operation to all frozen weights of the teacher and the student. Next, we calculate the scaling loss as defined for all classification and regression heads. And then we update the scaling parameters using gradient descent. Finally, we update the weights of both teacher and student networks after m iterations using our updating rules. The representation disagreement aims to encourage the student to explore further underlying patterns in unlabeled data during the SSL stage. To achieve this, we begin by computing probability distribution of semantic representation from both teacher and student. Next, we calculate asymmetric KL divergence between these probability distribution. Finally, we incorporate these laws along with the unsupervised laws to update the weights of the student. We conducted a comprehensive evaluation of our proposed method using COCO and Pascal VOC datasets. The experimental results are quite impressive, especially our proposed approach surpasses the baseline unbiased teacher version 2 by an average MAP margin of 2.2 and 2.1 on COCO-standard and COCO-additional dataset, respectively. In addition, our proposed approach outperforms the baseline unbiased teacher version 2 by an average MAP margin of 3.3 on the Pascal VOC dataset. We conducted extensive ablation analysis to showcase the efficacy of our TMR stage and RD strategy. These evaluations emphasize the versatility of our proposed approach and demonstrate how the RD strategy promotes mutual learning between two models and enhance model distinctiveness. In conclusion, our approach can be integrated into existing semi-supervised object detection methods that follow the common approach. It improves performance and generalization, facilitates the transfer of reliable knowledge from a student to teacher, and prunes noisy student weights. The TMR stage dynamically refined the models, preventing overfitting and retaining learned pattern from unlabeled data. Also, the RD strategy alleviates consensus problem, prevents early convergence, and promotes model distinctiveness by exploring more underlying patterns in unlabeled data. Our extensive empirical experiments demonstrate the superior performance of our proposed method over state-of-the-art methods. Thank you for your attention.